Um, I took the syllabus that was there in your, give me a second, let me show you that one. I'll say share my Word document. Where is the word here? Okay, other applications. I cannot see that. Give me a second. Why I'm not able to see the document that I opened. Okay, so this is your syllabus sheet. I like your red shirt, Chakravarti garu. Red or maroon? It looks red here. So, oh no, very good. Looks great. So the unit one, so you can see here preliminaries of algorithms. We kind of covered some of those things like at a rapid pace, right? Sorry, okay, I'm getting static. Mute yourself, please. Whoever joined just now. So I took the that and I kind of put them here. So this is what unit one is, right? So, and then I started putting together a bunch of things there. So this class, we'll go through that formally, what we have done. The trick to learning is to rehash what we have learned earlier formally or in different ways. So it's like pretty much repeating what we have learned almost every single class. So that way, by end of the course, it would be ingrained in your mind. Okay, it's called hardwiring your brain cells. So that is what happens here. So some of these things, when I go through formally, it covers what we have done earlier. It keeps giving you a new perspective to that, and then we add on to it. Okay, so having said that, I will continue with the presentation, and in approximately at midpoint during the class, we'll take our regular 3-minute break for you to stretch yourself, and then I'll get my tea again. For those of you who want to know, this is a long weekend in US. It's called the July 4th long weekend. And I'm talking to you from my hotel room in Southern California. I drove here again with my sons and to be with my daughter. We picked up our other daughter from the university where she's doing a program, summer program. They're high schoolers. So this weekend is a family reunion for us in lovely Irvine, which is close to Disneyland. Okay, great. So here we go. What is an algorithm, right? We said kind of steps, right? I showed you some picture. That's what this is. Sequence of unambiguous instructions. See the keyword there, unambiguous. Okay. And then, so we have a problem that is given. We come up with an algorithm, and then we implement that in a computer where there is an input and there's an output. Typical way, right? Let me put it in a slide mode here. Are you all able to see the slide well? Okay, I'm trying to arrange my screens here so that way I can see everyone. Okay. So here is an example. Okay. You all remember this famous guy Euclid, right? Famous mathematician. Okay. We talk about Euclidean geometry and all that stuff. So here is a problem called GCD. GCD ante greatest common divisor. Okay. Now you must be wondering, hey, my God, we are learning math now. Yeah, but it gives a good example of what an algorithm is, right? So we're finding the GCD of two non-negative numbers, given two non-negative numbers. What is the greatest common divisor, right? So the two numbers given are m and n. So for example, GCD of 60 and 24 is 12. I think you remember from your middle school math what GCD is, right? So What is GCD of 0, 0? Can somebody answer that? Oh, that's a nice car horn sound. On GCD of 0, 0 into 0, no? I don't know. You tell me, I'll put the answer there, okay? Now, so what is the algorithm there? You see, Euclid's algorithm to solve that problem. The algorithm basically is we are doing a repeated application of equality. So we do GCD mn equal to GCD n comma m mod n. You know what mod is, right? When you do a mod, you get the remainder. That is the result. Okay? And we keep doing that until the second number becomes 0. So if you go down here, that's what you see here, right? GCD of 6024. So we take GCD equal to GCD 2412 because you take the n, right? And then you divide 60 divided by 24. When you do that, 2 times 24 is 48, and then you get remainder 12. Then you continue the same thing. Then you take 12 in the first term, and then 24 mod 12 is 0. Okay, so whatever is remaining, that becomes your greatest common divisor. So that is the algorithm. So you have a problem, and then you're trying to come up with a solution. So this shows you the algorithm there. Thank you, SVCW for saying, yeah, 0. GCD of 0, 0 is 0. Okay. Now, so you can see, we also said that when you're writing the algorithm, you're writing them as kind of pseudocode. Remember, we talked about pseudocode, steps, combination of English slash, using some constructs like while, if, then, else, and things like that. So you can see how he has described that Euclid's algorithm. Okay, step 1, if n equal to 0, return m and stop. Otherwise, go to step 2. Okay, so, and what do you do in step 2? Okay, Chakravarti Garu once again put the thing here. If anyone is having technical problems, call him up. Okay, great. Worst case, you can always disturb and no problem. We'll try to solve the problem. Thank you for your message there. Okay, so you can see here, so we know the GCD, and I'm trying to write a program to execute in a computer. So whoever is the algorithmic designer here, he gave these steps. So couple of things to note here is, the guy who is giving the steps may not be the same guy who is executing or who is writing the actual program. Okay, this could be one person, and the actual program writing could be another person. It could be the same or it could be different. It's not like the same person has to do it. Okay, just keep that in mind. Okay. Getting some static. Let me stop sharing. Okay, I muted all. That way I will not hear the static along with the rest of the class. Let me go back to sharing my screen again. I'm not putting it in presentation mode. If you cannot see it, I'll put it in presentation mode. I better control this way by showing it in a slide mode only. Okay, great. So you can see here, there are other methods of computing the GCD, right? So here is another way of doing it. Okay, now I'm not going to read you all the steps as to how to do it, okay? But there's another way of doing it. Okay, suffice to say there's a second way of doing it. And then there is a third way of doing it, okay, which is taught in middle school. At least in US, it is taught in middle school. Now, since it is taught in middle school, I would have forgotten whatever I've learned in middle school, right? But here are some steps, okay? You find out the prime factorization. Prime factorization, all the prime numbers you're looking at there, right? You're looking at all the common prime factors. By the way, I can barely understand these steps, okay? I literally have to do it on a piece of paper to really understand, okay? The question asked here is this an algorithm? This is a procedure too. There's a step 1, step 2, step 3, step 4. Is this an algorithm? You can put your answer yes or no in the chat. Okay. I won't answer that. You can put it there and then we can discuss. Okay. Okay. So here is another problem. That was the GCD. So we learned this one, right? Sieve of Eratosthenes. This is like a prime numbers, right? Something to the prime numbers. So there's an algorithm here where it says, okay, list all the primes less than or equal to n. So given a number n, you are finding all the prime numbers up to n. Okay. So there's a solution to finding prime numbers. Okay. This is one way of doing it. Typically in middle school, or maybe even now, who knows, when we give this programming assignment, let's say I say, hey, list all the prime numbers from 1 to 100. How would you do that? Somebody can tell me, you can unmute yourself and tell me, how would you find the prime numbers? Given, let's say I want all prime numbers to 1 to 100. Typically what they do, they do it from they write the first for loop or while, while I is less than or equal to 100. And then they start doing it, divide by 2, right? Divide by 3 for the number up to some value. Brute force way, right? Here, I think it's a little bit more efficient. You really don't need to check all the way up to 100. You can stop at root n. Okay. Okay. I will put it in the full screen mode here. That is the full screen mode. Okay. So there are different ways, right? Some people know how to write very efficient algorithms, and some people know not the most efficient, but reasonably good way, and some people really don't know how to write algorithms. Okay. The goal is to learn how to write good algorithms too, hopefully as part of going through the class. And the moment I say good algorithms, that's where the entire data structures class comes into existence. Choosing the right data structure is part of an algorithm, in my opinion, and choosing the right way to solve a problem also is part of that. And then whether it's a good algorithm or a not so good algorithm is analyzed using our time complexity and space complexity. Okay. Okay. That is the reason why we study algorithms, right? There's a lot of importance for that. You always want to come up with elegant solutions. Okay. There's a theoretical importance to it. And this is the essence of computer science. We stress that even in our very first class, saying that if there is one subject that is the most important subject that you learn in this course or in the entire computer science curriculum, it is data structures. Okay, I have to mute all again. Okay, I will do so. In order to mute, first I have to do stop sharing. Then only I can go and mute all. Okay. Okay, I have muted all. I'll go back to sharing now. And I'll put it in the presentation mode. Somebody has a question, put it in the chat. Okay. So we study them because of their importance and then practicality, right? Uh, you want to write piece of code which is efficient. Otherwise, what happens? Let's say you're writing an online application where people are logging into your website. Let's say simple thing as login. Okay, and then the way of verifying the login, authentication అవన్నీ ఉంటాయి, authentication authorization అవన్నీ. If you don't write the code well, the guy is staring at the screen because the next screen is not coming up because your code is still trying to validate what he has entered. Right? So from a practicality viewpoint, you want to write code so that way the user is quickly logged in and then the next set of screen is displayed and he will do whatever he needs to do. Okay. So that is why we need to study algorithms. So you have to live, eat, breathe, sleep, dream, everything algorithms in this class. Once you do that, then you become good algorithmic designers and the rest of your life would be easy. And you earn big bucks too. Now, one more time, I'll reiterate, right? A good algorithmic writer is not necessarily a good programmer in terms of coding, when I say programming, okay? Keep that in mind, okay? By the way, on a scale of 1 to 10, I don't know how much your professors there listening to this would give themselves in terms of programming knowledge, who can do coding, okay? I can tell you on a scale of 1 to 10 today, if you ask my children, they'll probably give me a 4. They say, let's not disappoint Papa, let's be nice to him. Of course, if you ask me, I would give myself more like a 6 or a 7 in terms of writing code. But when it comes to designing algorithms for a problem, or when I solve enterprise level problems at an architecture level, I work with the IT and all that to come up with pretty good algorithms to solve a problem. So at that, in terms of algorithmic level, I can give myself an 8 or a 9. I think I would say 8. I'm getting old now. My brain doesn't work as fast as the young kids' things are, right? So it doesn't have to be one and the same. Okay, keep that in mind. Okay, now, two main issues related to algorithms are how do you go about designing it, right? Where do we get those thoughts, right? We have to figure out how to do that. And then how do you analyze the algorithm? These are the two most important things. We covered again, last class also we covered, but we did a sweeping broad overview of those things, okay? Here we are doing it in a little bit more systematic way. Now we start formalizing stuff because I introduced you some things, got your feet wet. Now we are learning it formally, okay? So when you take the advanced class, we will learn some of these design techniques and strategies more formally and more in depth. Here you're getting an appetizer. This class is like an appetizer for you. The real analysis of algorithms class is the next one. This just sets the stage for you, okay? So here are some of the techniques that we learn. Brute force method, divide and conquer. Okay, there's something called decrease and conquer, transform and conquer. We analyze a lot of space and time trade-offs. So within the overall framework, the strategies that we use are listed on the right, called greedy approach. I'll give you some examples of that as we go along. We do some dynamic programming, okay? Big buzzword, okay? We write algorithms where we improve things iteratively. We do backtracking algorithms. We learn backtracking, like if you take a chess problem, like placing 8 queens on a chessboard. The classic way of coming up with a solution for this is backtracking. You take one step forward, you analyze whether that step is the right step in terms of arriving at your solution. If not, backtrack to the previous iteration. So there are some ways of doing that formally. We'll do those kinds of things. And then finally, of course, there's something called a branch and bound. Because if you have lots of branches that you can test, as you're testing them for completeness of a solution, if there's no solution, you bound it. So that way you don't have to revisit that. So there are ways of doing that. So those are all the formal ways of applying strategies. Okay, Ravi Kiran has raised a hand. Okay, go ahead, Ravi Kiran, put your question in the chat. And Ravi Kiran, where are you from? Which college you put it there? And then I'll read your chat and then I'll answer the question. Okay. In the meantime, I'll continue. Okay. So going to this analysis of algorithms, as we touched upon last class too, we talk about time efficiency and we talk about space efficiency. Most often time efficiency is where we focus on, and we get into what are known as the worst case analysis, best case analysis, right? And optimistic analysis. And in that context, again, we talk about the big O notation, okay? Big O, omega and theta notation. So we look at those kinds of things, okay? Ravi Kiran, you have difficulty putting in chat or you raised your hand. So go ahead and put your question in the chat. Okay. So where do we apply all of these things? In the entire computer science and programming literature, these are the kind of things that we do. Okay. Like as a good friend of mine tells me, programming is all about searching and sorting. We do a lot of search techniques. Okay. Now, for those of you who have written your C programs in your C programming class, you know we also do string processing, right? That's another problem type. We have graph problems. Graph problems are all over the place. Whether you talk about enterprise resource planning solutions, whether you talk about, let's say, India is booming with airline industry, other than Malia's Airlines, of course. The way they route the planes, it's a typical graph problem. So how do you route a plane from A to B to C to D in an optimal fashion? What is the optimal fashion there? It could be in terms of the shortest distance between the flights or total distance covered, least fuel consumption. There's some criteria. Okay. Any kind of combinatorial problems, we solve them using algorithms. Geometry, of course, we know that. And numerical problems, right? Scientific problems. All these are different problem types where writing the right algorithms becomes fundamentally important. Okay. Let me pause there and ask question. Do you have any questions so far? I know only one person raised a hand. I thought they had some question, but I didn't see the question put in the chat. Okay. So those are all the classical problem types. Now, the fundamental, basic, essential things that we have to use this data structure, right? Ultimately, we process data. And the way you store that, the system gives you some concrete data types. We talked about data types, right? Like integer, char, all of those things last class. So we have these data types. Some of them are listed here. There are different types of lists, right? Everyone understands the concept of a list in English. And the list is manifested as an array or a linked list. It could be a string, stack, queue, priority queue. Okay. These are all different data structures that we talk about. Then we get into graphs. All these things are kind of manifest themselves as graphs, trees, sets, you name it, right? These are all the types of things that we cover. We may not cover all of these things in this class, meaning in this course, not class, in this course, but we'll cover the fundamental stuff here. And for advanced things, you have the next class. Okay. So far, still no questions. I'm surprised. Either I lost all the audience or they're just quiet. Let me ask you a question again. Are you all able to hear me well? Or did I lose the audience and I'm just talking to myself? Okay, I'm glad. If Chakravarti Garu can hear me well, that means I know at least I have an audience of one who is hearing me. That makes me very excited to continue, right? Okay. Let me pause here, enjoy my a sip of tea here. So what we'll do is, right, we will take a little bit of time and then Vanati, okay, got it. Vanati College said they are able to hear, that's good. PSCMR, they said yes. Okay, very nice. I think somehow magically most of the colleges there solve the audio video problems, looks like it. So I should pause here. It's kind of funny that, okay, that is Vanati madam is from Aditya College. Thank you, Andy. Okay. It's so funny. There's always resistance to digressing here for a second. There's always resistance to experimentation. I noticed that in many institutions or in all walks of life, even the industry, in Cisco, right? When we started MOOCs more than a year ago, you would not believe it. Compared to now, it was so bad last time when we first started. Audio doesn't work, the connection doesn't work, people are frustrated. Students don't know how to go create their accounts in Lensu. Faculty members are resistant because, hey, why do you want to do that? It's nice to do it in a classroom, right, in front of the students. And of course, all the other standard university politics, right? Some professors don't want to do it. They want status quo, and some professors say, no, let's do it. So I have seen all kinds of those scenarios when we first started, okay? We had lengthy discussions, okay? And then they said, no, we don't want any more MOOCs. But somehow we survived, okay? So in that sense, you should all consider yourself as pioneers in this, right? So there will be problems. Don't you think there are problems in a physical classroom? I will give you an example of how I learned a very important subject in my life. My batch was the first computer science batch in the country, okay? After I graduated, I happened to work for Defense Labs under Abdul Kalam, and you know who he is. He was my boss, okay? Now, how did I learn computer networks in my master's in computer science? That was the first batch. So I had this professor, I won't take names, it won't look nice. So he used to bring the book on computer networks by Tannenbaum. Okay, very famous book by Tannenbaum, Computer Networks. I became so good at it, I knew pretty much every paragraph on which page it was listed, in which chapter. I was that good in those days. Now, how did I learn that subject? The professor used to come, write down on a blackboard, no PPTs and no nothing, write down on a blackboard, literally from the textbook onto the blackboard, and then read out what he has written on the blackboard. Okay. So you have a textbook, you write page number 1 of the textbook onto blackboard. Fantastic writing though. One-on-one presentation there. We are in a classroom. We have come a little far from that type of learning. This is fun. So if you embrace change, you will enjoy it. Okay. And you will learn. Just felt like reiterating that. And faculty members, that's why I want you to add to the class. I want you to participate, and in the sense that you are teaching along with me. It's not me teaching. We are all teaching together, learning from each other. Okay. So keep that in mind, because for me to talk for 2 hours without any interaction is quite boring. But that's not what MOOCs and collaborative learning is about. A lot of interaction needs to be there, both inside the classroom and outside the classroom. Okay, that much for the digression. Let's jump back to the presentation now. Arrays. Now I'm now getting into, slowly I'm introducing the data structures, right? Now students, you might be thinking, hey, we already did C programming. You all know what an array is, right? That's what you must be thinking. Why am I learning what an array is? Just to formalize stuff here, right? For those of you who know it, great. For those of you who do not know it, here is your opportunity to know what an array is. Now, I have seen students both here in US and in India who have done programming classes. When they come to a data structures class, they would have difficulty even understanding arrays. Okay, that's why it's always good to start from the beginning and then build on it. Okay. So it's a structure. The fundamental thing about an array is there's some structure where all related elements can be stored together. Okay. And then second bullet, you have to take it with a grain of salt. It's the same size throughout program. Not quite true in the modern computer science way. I can build dynamic arrays, right? By allocating memory from heap. But let's assume that, because typically when you declare an array, normal way in a programming language, you say A10. That means that array A has 10 elements. That's, in that sense, the second bullet is correct. Okay. Now, a little bit more formally, because I think I don't have control over your exams, right? So in your internal exam or whatever, they might ask you some more formal definitions. Okay. In that sense, here is a little bit more formal definition. Okay. In my exams, I don't ask definitions. I give them problems to solve. Okay. So here is a more formal definition. It's a sequenced collection of variables. That's number one. Number two, all of them are of the same type. Okay. You cannot have an array where one element is integer, one element is char, one element is string, not like that. They all have the same data type. Okay. And then wherever there's an array, to traverse the array, as you know, we need some kind of an indexing mechanism. Okay. So you have like indexing mechanism. Since we are computer scientists, our numbering starts from 0. So we have an array A here. These are all the elements, and the way to index it, we say A0, A1, A2, and so on. Okay. Just out of curiosity, let me ask a question here, so that way I can bring out some participation instead of me talking, right? In C programming language, I'm putting it in chat here, you can see it. Let's say you have an array of size 50. Okay. I call it A50. Now I write a program. If I write a program, to write element to store 100 elements in this array. Okay, it's a array is 50, but I'm asking you to write a program to store 100 elements in this array. What is the behavior of the program? What would happen? Faculty members, please feel free to pitch in there. Let's have some fun here with the students here. I did not really define precisely, but The only thing precisely that I defined is I declared a 50 element array and I'm asking you to write 100 elements into that array. What kind of behavior the program would exhibit? And your code has compiled and you have an executable. Okay. Okay. Jntuk Kakinada answer, only 50 will be taken. That means, okay, hold your thought there. And somebody said like it's overflow. So it's going to overflow. What exactly is going to overflow then? Continue. You mean the array will overflow. We call it buffer overflow, right? I think you're alluding to buffer overflow. If the so that means you are basically saying that the buffer would overflow when all the 100 elements are listed there, right? Now, how would we prevent that instead of having buffer overflow? How would you write a program where this scenario would not even occur? What kind of algorithm you would have where when you declare an array, you would ensure that no one can write more than 50? Okay. Using dynamic, no, we are saying it is a static array. We are assuming it's a static array. It is size 50. There is no dynamic memory allocation. We are already assuming it's static 50. Now, Holia thought Jntuk Kakinada, I want others to respond there. And I'm assuming these are students who are responding. Faculty also can respond. I already said that. How would you prevent an overflow? And remember, I already told you that it is it's in C programming language. I already prefaced the question with saying in C. Because if you take an object-oriented language like a Java or a C++, the system automatically prevents this from happening. So in C, what do you do to prevent that? In your code, you will probably write some condition, right? Whenever you're trying to insert into an element of array, you'll make sure it is inserted in less than or equal to 50th location, right? If the loop is for I equal to 1 to 100, and then you say ai equal to some value, you will check the value of I, right, before you insert. Yes, you will get if you don't write that code, then you will ultimately get the segmentation fault. You're absolutely right. Core dump or any unexpected behavior, right? So in C, a good programmer or a good algorithm guy, he would say, okay, we are going to save these things in array, but before an element is inserted, we are going to check against the array bounds. So what we do is called bounds checking. Okay, all the answers are right there. So to prevent these things from happening, we do what is known as bounds checking. Because C programming language, the language did not define that. C is very powerful, but it's also notorious in terms of what kind of bad code we can write. Okay, so the program has to write it their own bounds checking in C. And these things become more important in today's world. Your professors would have, in terms of introducing you to computer science, would have told you that there's something called cyber security. Okay, you probably, actually they asked me to teach cyber security class this semester. We had a lot of discussions. We said after you guys are introduced to some courses, I can teach cyber security. lot of security. Why am I bringing cybersecurity into data structures and algorithms class, right? When I teach secure programming, we show examples as to how hackers exploit poor programming practices, like people declaring array and not checking bounds. Okay, they don't write the validation code for array bounds checking. Okay, and as somebody put here, usually there'll be a segmented fault or code dumped, but hackers have clever way where they overwrite, but they ensure that there is no segmentation fault. They don't want the system to crash. Okay, they would probe it to the extent where they can find a return pointer. You probably learned these concepts in your computer class, first class in computers, how the programs are built in the stack. There is a return pointer. So they are looking at your return pointer to see if they can access that memory location and change the return pointer to their site. Okay. Now, some of you, I don't know if you have learned these concepts or you remember those things. Those are the type of thing that would happen. And the most notorious culprit in all those hacking attacks is an array, and whether the programmer has written array bound checking or not. Okay. Okay. Going back here now to the class. What we do typically is, okay, we want to basically know not only the array, but also what we call it as the array length and capacity. Okay. So in Java, when you take the Java programming language, Java is an object-oriented language. So when you declare an array becomes an object. What do objects have? They have methods. That length is a method. So you can call up a.length. Okay. Compare against the a.length, and then ensure that these kinds of overflows would not happen. Okay. Very fundamental data structure, array. Okay. Now, how do you see it? I mean, in my advanced class, we will simply say array and then we move on, right? But this is your almost like a beginner's class for you. So I have to be a little bit more formal in terms of showing you a few extra details. So what exactly is happening when you're declaring an array? This is what is happening. It is nothing but it is a group of consecutive memory locations. Okay. What do we mean by consecutive? That means 1, 2, 3, 4, 5, 6, 7 a memory low, they'll be contiguous. Okay. And now, does contiguous mean that in the operating system's perspective, I don't know if you people have already done operating systems or not. Are they literally contiguous in memory in your RAM? Or is it a logical contiguousness? The question may be a bouncer to the students, but faculty members, you're welcome to assist us. As far as the program is concerned, they're contiguous. Okay, that's why we say C0. That is the 0th memory location, and from there, all the elements are stored one by one by one by one like that. Okay. Okay, that's what we mean by contiguous. Okay. Now to access those things, we specify the array name. They don't have OS subject till now. Thank you for letting me know. When you take the operating systems class, we will get into details about what contiguous memory is. These are pages which are linked. There are a lot of concepts that are introduced to you. But as far as this class is concerned, let's assume they're contiguous, meaning sequential. Okay, one after one after one like that. Okay. So how do you access them? For those of you who have truly learned C programming, you know that. We say if the array is C, that is the array name, C0, C1, and so on. And when you say C50, these numbers go from C0 to C49. Remember, we start from 0. Okay. So that's why you see at the end here, we say C0, C1 up to Cn minus 1. Okay. Now students, I'm assuming you're following me and if If you have any questions, again, tell your facilitators there to put your question in the chat. So here is what you have done in your C programming class, right? Array U3 to C0. Okay. And then what is the next statement? It is printing, right? I forgot my C programming language, but there's some small things I remember here and there. Then you want to display that. What is the value in that? You say printf, that is the command, right? If you use my object-oriented language, C++ or Java, we say C in and C out. Okay. Decimal, and then you're telling to the system, print the first element of the array. Okay. Now you can also do a lot of esoteric things in C. Like C, for example, the index doesn't need to be a constant. It can be an arithmetic expression. C5 minus 2. Okay. And then he's doing some, if x equal to 3, then you do something. Okay. So there are some fancy ways of manipulating arrays. Okay. And this is how you declare the array. Now notice something here. Remember in the very first class I said, slowly I'll make you write whatever you learn here in your programming language that you know. That was the reason I thought, let me start giving you a little bit of C flavor there in case you have forgotten or you have not learned it the first time. Okay. So once you declare, you can see in the examples there, right? You declare in different ways. And then once you declare, you save them and then you print, manipulate, whatever, right? And you say integer C10 means you're storing integer numbers. If you say float my array, you're storing float, decimal numbers. Okay. Okay, that is that. By the way, faculty members, don't take everything that I say as true, okay? Sometimes I do make mistakes, so please feel free to correct me, okay? And if I make a mistake and you correct me, I'll say, yeah, I just had 2 glasses of wine or something, and then my mind is not working in the middle of the night, right? And that's just a joke. I don't drink actually. Okay. What else? Here are different ways, students, right? See, we are combining. You cannot teach a data structures class all theory without showing some examples of programming. Okay. So here are some ways. Refresher. You are initializing a integer array of 5 there, storing 1, 2, 3, 4, 5. Okay. Now, if there are not enough initializers, students, you may or may not remember, the rest of the elements of the array are initialized to 0. Okay. What else it says here? If too many syntax errors produced, I don't know what that bullet means here. Okay. If too many syntax errors produced, okay. So if you declare integer n5 and you give 10 elements, it gives you a syntax error. Okay. C arrays have no bounds checking. We covered that. Okay. Size is omitted, then initialize determine the size. Okay. There are some simple things there. Okay. Now, when you have those things, remember we said that it's all about data structures, and then so see how I'm taking a functional unit of showing you a data structure and showing you some sorting and searching in that data structure. It's not like I'll follow the same technique next class also. I'll follow a different technique to teach some of these concepts. Okay. There's no one way to teach them, multiple ways. Okay. So now when you have an array, most often we try to sort the data. Okay. Whether it is like all of you have used an Excel spreadsheet, right? When you do the data filtering there in an Excel spreadsheet, what do? We can go there and there'll be a drop down. I say ascending order, descending order, alphabetical, I can sort based on type of the data. There are different ways of sorting the data. Okay, but here let's keep it simple. Okay, we are given a list of array items, as you can see at the bottom. Example, you are given 3, 4, 2, 6, 1 in an array, and I say write a program to sort that array. Okay. Now, have you done sorting of an array in C programming language? You can answer that. Am I seeing video of the people today? Let me see this one here. Participants. Aditya, who has the, okay, Jntuk Moocs is, I see the picture. Let me see, do I see picture? Divya, R. Divya. I don't know which college is that, you can speak up. JNTV, let's see, do I see picture of JNTV? I don't see it yet. SVCW, let's start there. I can see their picture barely. Have you written, let me ask SVCW, have you written C programming examples to sort arrays in your class? You can just raise your hands if you have done it. I can barely see them. Okay, or you can put it in chat. Yes, sir. Excellent. You have all written. Okay. Now the next question is, what sort was implemented? The next question, yes, I see a lot of people saying they have written sort algorithms. Okay. R. Divya, they said they have implemented bubble sort. There you go. Okay. So that is what we are showing here, right? How does the bubble sort work here? You can see in the slide, right? Then I'm seeing a nice picture of DMSSVHCE. Show of hands here. How many of you have written bubble sort in your C programming class? Don't be shy. I'm seeing boys and girls in some kind of uniform there. Raise your hand if you have written in your C programming language class. Don't feel shy, okay? Even if your faculty member is there, don't worry about him or her. You have to raise your hands a little bit tall, because if you raise only this much, I can't see. You have to raise your hand. Okay. Okay. So if I were to ask you to write a bubble sort algorithm now in the class, would you be able to write the algorithm on a piece of paper without looking at any book? If you can write it, then you can do that. Or letters. Yeah. That is my, okay, I can do that. Bear with, I'll do that. Give me a second, okay? I'll increase the chinnagane on mare. I have my presentation mode here. Okay, let me do escape here. Okay, give me a second. Let me increase the, I think I'll increase it to 20. Is that better? It kind of overflows the screen. I increase the font size. Hopefully you can read it. Right? So they only said they only wrote, oh, just now I got feedback from one of the faculty members regarding this. Letters not visible. Okay. I increased it. Okay. Okay. Let me say thank you to the thank you was meant to Chakravarti Garu. Okay. So these terms are what I heard was some of these terms might be new to you. So let's go slow. That the reason here is I want to go slow. Okay. So that everyone understands. Some of you have written C programming because you have done that, where you sort. What does sorting means? To arrange them in certain order, right? That everyone understands, right? I don't have to redefine sorting. That's a standard term. Uh, Same thing like let us say if I have a group of students who are let's say you're taking a group photo. Okay, I don't know if your instructor professor takes a group photo at the end of the class with all the students. I think they probably will in a selfie or right. We always tell them, hey, shorter students in the front, slightly taller students in the middle, and really the tallest students in the back, right? For a photographer to take the picture of all the faces, correct? That is a sorting. That's a practical example of sorting. Okay. Now, there are multiple ways of doing that sorting. One of the classic ways of sorting, that's the reason why I asked you, hey, do you write sorting in C? If so, what sort it is? There's a technique called bubble sort. Every student learns how to write a bubble sort. Okay. So how is that happening? The way you write the program there, if you go down here, let me put it in a mode here. 1 second. Let me try to increase the size here. Bear with me for a second. Come on. Let me take this here. I'm increasing the size here. We'll increase just that part for now a little bit more. So if you look at bubble sort here, you're 1 second, mute yourself, please. Whoever unmuted, mute yourself right away. Thank you. So here is a bubble sort, right? It's an algorithm. So what does it say? You go through the array, you do several passes, right? So in every pass, meaning you're comparing the successive pairs of elements. Okay. If they're already in increasing order, you don't do any change. If they're in decreasing order, you exchange the elements, high level algorithm, and you repeat throughout the array. So when you go here, 1 second, and if somebody has to unmute yourself. Let me mute them and then share. Okay, I muted you again. Let me share my screen. Okay, so when you see here, the original list that is given is 3, 4, 2, 6, 7. Okay, so I mean, you probably may not remember the algorithm totally. That's why when we do these things, at the very beginning, even Murthy Garu and Chakravarti Garu were telling, if you recall, hey, whatever you learn, go try to implement it in the language that you learned or whatever language that you're learning now. Okay, so this is how bubble sort works. Originally, you're given 3, 4, 2, 6, 7. At the end of the first iteration, these things move, right? You can see 2 and 4 swapped, they swap places, right? At the end of second iteration, you can see 2 and 3 swap places, right? So there's an order in which these things are happening. Understood? You don't need to know the exact algorithm right away, but at a high level you understand, right? So at the end of it, as the slide is showing you, every pass, the one number is going through some kind of swapping. Got it? Okay. I do see the Chaitanya student looking totally confused. The young lady there, but it's okay. We learn initially it'll be all confusing. Okay, but don't worry too much about it. But the idea here is there's some technique called bubble. Okay, that is the concept there. We'll come back to bubble sort. It's a very famous sort, right? Okay. Now that is sorting. Now what is searching? Searching means you're searching for an element, right? If I have an array of students, Mary and Tom, Chakravarti Garu, Murthy Garu, all of these guys in an array, and I can search for a particular faculty member in that array. That is searching, right? So if I have a 100 element array, I can search that array for a key value. Key value is what name I'm looking for in a name array. Okay. So what are you doing? You're taking the name and you are saying it's a 100 element array. You say for I equal to 1 to 100, if AI equal to Tom, you found your key. It's successful. Okay. Typically, it's great when the array is unsorted. Okay. And then the worst case, the element could be the value that you're looking for could be in the 100th index. Worst case. Best case, it could be in the first element. You found it, you hit the jackpot, you're done. On average, it's about half of it, right? Somewhere around the 50th. That's the law of averages we call. Okay. Very simple example that illustrates the worst case, best case, and average case. Okay. Now, what we do when we are doing searching of arrays, there's another technique called binary search. Okay. Binary search means what they do is, first of all, the array is sorted. That means it is some order. Let's assume it's an array of numbers. It is one, and the numbers are sorted ascending. Okay. Let's say the numbers are like 1, 2, 3, 4, 5 up to 100. Okay. Now you are saying, okay, I'm looking for a number called 55. So when I have to look for it in the binary search, since it is sorted, I go to the 50th element of the array and say, hey, does it have the number 55? If it has it, great. If not, you know whether to see the right side of the array because it's a sorted array, right? And you eliminate one half of the array. Then you do the same algorithm. Check. So you eliminate 50 elements, 50 indices. Now you are left with 50. Now you take the middle of that. Again, you check. Would the 55 fall left of it or right of it or same? You continue that. That is called a binary search. What you're doing basically there is you're reducing fast, right? You can do a quick search of that. If you do a sequential search of a sorted array, it'll take more time, right? You use a different type of sorting technique called binary search, not sorting, searching technique called binary search as opposed to linear search. And you arrive at a solution faster. Okay. So what I want you to appreciate here is the different nuances of solving a problem. Okay. It is not like there's one technique that will work for every single time. It depends on the data. It depends on what is it that you're trying to do. There are multiple parameters which dictate how you want to store the data, what is the data structure that you use, and what is the solution that you use to tackle the problem. Okay. Okay. Now let me move on. So a little bit more into analysis of algorithms. Okay. So the time now is, I think I need to take my wonderful 1 hour. I didn't stop at the end of 1 hour, but let's take a stretch break of about 3 minutes and we'll be back in 3 minutes. Okay. I'll put you on mute and then I will go get I'll stop sharing. I will write here saying that it is a 3-minute STRETCH anukunta spelling. Okay, 3-minute stretch break. We used to do yoga in our classes when we started MOOCs. We all used to do some 3-minute stand up, do some exercise, go get your coffee. Okay, see you in 3 minutes. 33 years. I was a young man in those days, and I used to date my wife, who is my wife now. She was my girlfriend in those days. Okay, very interesting story. Yeah, and I used to be a scientist, government of India, right? So, and she used to work at CMC. She is a gold medalist and all that. So I used to meet her in the evening, and then I used to guess what I used to do, right? I say, hey, I just have this just 2 hour class to teach. Let's go to the class. So she used to come and sit patiently in the classroom when I was teaching data structures or programming, databases. And then 2 hours stretches to 3 hours because class అయిపోయిన తర్వాత all the students used to gather around me. We used to talk a lot. You can imagine what happens after I left the classroom where I have a very unhappy girlfriend saying that I extended the time from 2 to 3 hours. And then she used to tell me, I know why you stretched it to 3 hours because there are a lot of pretty girls there and you wanted to spend more time with them. You can imagine the fights that we used to have on that. But that is my first love for teaching. I think she finally understood it's not the girls I was after there. I love teaching. Okay. I'll share with you a lot of stories like that as we go along. Okay. I do see somebody in Kite B2 talking to the students. Should I go ahead and start the lecture? Once that gentleman professor or coordinator stops, I can start my lecture. Okay, I'm starting my lecture. I think I've already unmuted myself. Okay, I'll simply say 1 second, bear with me. Yeah, you can hear. Participants, yeah, you can hear me. I'm going to mute rest of you. Let's continue with our lecture. Okay, analysis of algorithms. Let me put it in the presentation mode. Okay, nice picture there. For those of you who are wondering, the slides, I pull slides from different sources. Sometimes I see you can see where the source is, sometimes you don't. But I do take a lot of liberty of pulling a lot of slides from different sources because I have access to these things as a professor here. Okay. So when you're talking about analysis of algorithms, okay, what do the algorithms do? They transform input to output. That is the processing, right? So when you have more input, the running time of an algorithm typically grows. Typically, everything you have to take it with a grain of salt. Okay, processing 1,000 records takes less time than processing 1,000,000 records, right? And then to determine the average case, in general, from a theoretical viewpoint, it's a little bit difficult. So what we do in analyzing the algorithms, we focus on the worst case analysis. The reason, of course, is it's easier to analyze. Now, it's all theory for you at this point. But as we go along, you'll appreciate what we mean by that. That is the big O notation that we are going to adopt. That shows the worst case analysis. Okay. Even in real life, we always say when you go to these meetings or even amongst your friends, right? Hey, what is the worst that can happen? That's a very common English language statement that we use. Even in computer algorithms also, we do the same thing. Okay. And that's very important in the case of gaming or financial applications and so on. Okay. 1 second. Okay. So now here are some studies, right? Some graph that shows you how we can do some of these things on varying input sizes by writing a program and measuring the time. Okay, so you can measure time. I do not know whether you have learned measuring time in your C programming, But here is a snippet of code which you can write in C programming language for any program that you write, how much time it takes to execute your program. So this is experiment, right? So that means you run lots and lots of runs, and based on, and you vary the input size, you'll get some kind of a graph. Based on that, you know what the average times are. Okay. Now, the problem with the experimentation is this one, right? Programs, as long if they are small programs, it's easy to write it and execute it. But a lot of times, to implement that algorithm and execute it, it's a little bit challenging. Let me put it that way. Okay. And then results may not be indicative of the running time on other types of inputs. It really depends on not just one type of input, different types of inputs, different patterns of inputs. All of those things would have some kind of an impact on the results. Okay. And then remember, somebody asked me the question, right, about these algorithms and hardware and environments. Both the hardware and the software environments have an impact too on the execution times of your algorithm. So we have to figure out a way where, instead of doing an experiment, looking at your algorithm, we should be able to determine which algorithm is better than the other one. If you take the bubble sort, for example, okay, there's another type of sort that we learn called quick sort. Okay, I don't need to run those two algorithms on data on a computer. I can look at those algorithms on a piece of paper and tell you which of those two algorithms is the right thing to use in the context, okay, without doing any experimentation. Okay, so that is what the theoretical analysis is. You use a high-level description of the algorithm. Okay, you faculty member, somebody is talking, and please mute yourself. Okay, so you characterize the running time as a function of the input size. Okay, and of course it does take into account all possible inputs, and then we can determine the speed of an algorithm independent of hardware and software environment. Of course, realizing that there will be some variations depending on the environment. Okay, so to show that algorithm, you write the pseudocode as we discussed earlier, and I'm reiterating that one. Okay, a little bit more structured than English, right? You saw like how I wrote while loop there, combining English with some language constructs that are given to us. Okay, definitely less detailed than a program, right? I'm not showing, okay, integer I, j, k, and all of those things. I'm not writing all the steps of the programming language. I'm using English. I'm using parts of the programming language terminology, and eliminating all the gory details. So I have to put a semicolon, I have to do this, I have to open parentheses. I don't put all of those things. That is why it is less detailed. Okay. Okay. So here are the techniques that we use to write our pseudocode. Okay. To show the control force, you use if then else, you have while do, repeat until, for, right? Different types of control statements. You have method declarations. Methods are nothing but functions, right? So say, okay, these are the functions, right? What is the input? What is the output? How you call the method, return. Okay, so these are all the things that we use to write the algorithm. Okay, let me see why I'm not able to. Give me a second. You lost my video. Okay. Thank you. Yeah. You lost the slide deck. You're seeing my slide deck, right? Okay, thank you. Let me go back to sharing my. Okay. Great. So Now, what are the functions that when we talk about analyzing these things, what are the functions that we typically see in our algorithmic analysis is this one. We say, hey, the algorithm can execute in a constant time. It can execute in a logarithmic time. N is the input size, remember? So it can execute linearly, it can execute n log n, or it can take n squared time. Okay. The moment you write a for loop, and then inside the for loop you have another for loop. How many you probably would have written a for loop statement in C, right? You say for I equal to 1 to 50, and inside that for loop you probably would have written another for loop saying for j equal to 1 to 25. Okay, like filling up a table. Let's say you have a table that you create. Table has xy coordinates, right? So you want to fill up table from A11 to A100, and then A21, A31 like that, right? It's a 2 by 2 table. And n by m by n dimensional table, you write two for loops to put the values. Okay. Uh, I will show you when we do the algorithmic analysis. We'll say that algorithm to fill out the table, two-dimensional table, will be of the order of n squared. That's where you get this n squared. You can have n cube and you can have n exponential. That's 2 raised to n. So which of these things is the least amount of time? If you ignore constant, if you see going from log n to this one, it increases the time. Log n is the best. So whenever you're looking at algorithms, when you analyze them, a log n based algorithm is much more efficient than either a linear or an n log n or n squared. Okay. So the trick is to write an algorithm which is close to log n. Not easy, but that is the trick. Okay. That is what distinguishes a great programmer from a not so great programmer. So when you're talking about data structures, it's really data structures and algorithms together. Data structures by themselves don't have any meaning. I wouldn't care less. You can choose the best data structure, but you have a poor algorithm to solve it, then it's no good. Okay. So whenever we are studying algorithms, we are looking at what is the running time. Is it of the order of constant or logarithmic or linear or quadratic and so on. Okay. Again, first few classes are still introduction, right? Once you start executing them, I'll actually make you uh, write some programs and tell me what is the order. For those of you who are mathematically inclined, this is how the graphs look like. Okay, for linear, constant, n log n, 2 raised to n. Okay. I hope your internal examiner will not ask you questions to show how the graphs look like. If they look like, carry this cheat sheet with you. The cheating చేయమని అనట్లేదు. Where did my slide go? I did something here. Hold on. Yeah. Okay, now I put it back in the presentation mode again. Okay. Keeping full screen again. So what are the when the way we do that is we are always looking at what are the primitive or the basic computations performed by an algorithm. Okay. And then we will identify that in pseudocode. Okay. And then we assume that whatever that primitive step is, it takes a constant amount of time from memory, because everything, remember, even though you are only second year students, I don't know if you have studied computer organization thoroughly or architecture as they call it. Every program that you write, it has to be brought from your hard disk into RAM. You all understand RAM now, right? You all carry cell phones. Cell phone has a RAM. Okay, that is random access memory. Only after it is obtained in memory that gets scheduled into the CPU, central processing unit, it gets executed. That is the flow of these programs. So RAM access is constant. That's what this is saying. Okay. So when these computations are performed, you assume a certain environment to understand this algorithm thing, right? If RAM, if one RAM location is easy to access than another RAM location, then your algorithmic analysis no longer works, right? That's why we say these are some parameters under which we assume certain things. They are all same for all algorithms. Then it makes it easy to analyze the algorithms. Okay. Now let me go to the next slide. So one way of analyzing algorithms is we say, hey, let's look at your code. Okay, how many primitive operations you have? Okay, now how many times you perform those primitive operations as a function of the input size? So we literally count the number of instructions that are there to say, okay, this algorithm has 100 times it has to execute this thing, whereas this other algorithm has 200 times it has to perform the operations. Then obviously the one that performs 100 times would be much easier, right? So how do we count? How do we determine what those primitive operations are? So you will learn those techniques in some of the examples that I'm going to provide to you. Okay. So if you see here, let me have to, if you, I don't know why, okay. If you see here, let me rearrange my screen slightly. Oh, last 1 minute? Oh, we are already done. Wow. Man, time flies. But let me wrap it up with this one particular example. So that way you can go home and dream about it. Okay. Increase the font size. ఇదేదో that Nagarjuna show laga, I have 1 minute to answer laga ondade. Milo evaru Kotishwarudu. For those of you who know Telugu, I think that is the show. So if you look at this piece of code here, it shows in step 3 how many operations are performed. Integer n equal to data dot length, right? Two operations. Step 4, some operations, a piece of code, and then you're seeing total operations performed. Okay, so I won't tell you how those numbers are listed there. This is your small take home, right? Go back, download the slide deck, convince yourself about the primitive operations by reviewing this particular slide. Okay, step 3, 2 ops, step 4, 2 ops, step 5, 2n operations. Step 5, the for loop, right? How did he arrive at 2n operation? So now I know when somebody executes this program, what is the total number of operations performed, right? You agree? Kada. It's pretty straightforward, right? So now you cannot do it on a large scale, but to begin with, you see a small algorithm like that, you can identify how many primitive operations are there. Whichever algorithm gives you the least number of operations, then that algorithm wins.
మీరు ఎలాగా లాగిన్ అవ్వాలో చూడండి అందరూ లిస్ట్ అవ్వరు
మేడం ఎవరో మాట్లాడుతున్నారు, ప్లీజ్ మ్యూట్ యువర్ సెల్ఫ్. Okay, so I will leave you with that thought. Next, because since my 1 minute is almost over, download this one, go log in or enroll yourself in the community, download the array, review what we have done so far. In particular, you come back next class and tell me that you understand this number of operations in this particular slide. Okay, so that concludes our lecture today. As always, I'll be online for as much time as you want if you have any questions. Okay. చక్రవర్తి గారు, మనము ఎండింగ్ చేసేటప్పుడు ఒక మంచి కోట్ ఇచ్చి పంపించాలి వాళ్ళకి, ఆర్ సమ్ గుడ్ స్టోరీ. నెక్స్ట్ టైం విల్ డూ దట్. ఓకే, ద క్లాస్ అఫీషియలీ ఎండ్స్ నౌ. And as I used to spend an extra hour with all the students, I'll be very happy to chat with you guys. If you have any questions, comments.